Good morning, afternoon, whenever you're watching this. If you're watching this, then good news. You're in week 4, statistics, normal distributions. That means it's just this week and the next week, and then you're done. Good job. In the meantime, just a couple of announcements. Since by the time you're watching this video, it'll be Monday, and that means that weeks 1, 2, and 3 are already in the gradebook, which means that I will not be accepting any late work because the deadline is the Sunday of every week. I am holding to that deadline, and if any work is attempted to be turned in that's already past due, I will leave uh, I will simply put a 0 next to that assignment and say that it's past due. So if you missed like 1 or 2 assignments last week, don't worry about them. Just move on to week 4 and make sure you get all the stuff from week 4 in on time. And a reminder, warm-ups are due the day that they are posted. Okay, with that out the way, let's get started. We are going to be doing normal distribution and statistics. Everything you've done so far has been leading to this. Normal distributions, there's 2 things you need to know about this. There's a couple definitions that I have here for you guys, right? These 2, normal distribution is a bell-shaped curve, symmetrical distribution with a tail on each end. A normal curve is the smaller intervals are symmetrical and the bell-shaped is a relative frequency histogram. The closer the shape, the closer it is to a normal curve. One of these definitions is referring to a data set. This is specifically referring to a data set. And you're going to see what I mean by that in the next slide. But a normal curve, what it's trying to say, it's when you have a population, like say you take a survey of how many people like, I don't know, Jolly Ranchers, and we say that it's normally distributed, right? That means that there is, most people are in the middle, like they are, okay, let me start over. The normal distribution just means that the number of people or the number of people that, for example, babies born with a certain baby weight, right? There's going to be, most of the children are going to be born kind of around the normal baby weight, and then there's going to be children who are born with a heavier weight and children born with a less weight. And in the example, this is actually the example that we're going to use in the next slide. Doctors have to use statistics to determine which is the healthy weight and which one is the not healthy weight in a population. Normal distribution just means that there is a pattern in that data, right? And it's evenly distributed across all sections. Sections are the standard deviation. That word should be familiar because you did it all last week. Normal curve is referring to 100%. It's referring to the area underneath the curve. So we have a curve like this, right? We have it broken down into sections. Don't worry, I'm going to draw a better one later. You don't have to copy this one. This was just to show you guys an example. All the area underneath the curve, all of this area, totals to 100%. Everything inside of that curve adds up to give you 100%. And the normal distributions, whatever numbers those are, whatever values, right? Whatever your values are going to be on top of the curve. Sorry about that. There's an ice cream truck passing, so hopefully you can hear me. Um, okay, sorry about that. Let's move on. So the values are on top of all this, and this is what you're going to be doing. Now, I have some more vocabulary words here. I have within, above, and below. Within just refers to all the percentages in between 2 points. Like let's say we have a point here and a point here. Now these lines are there on purpose. If I want to know what's the percent in between these 2 points, I'm really saying what's the percent, add whatever this percent is plus this percent, right? If I'm referring to above, that means that if I want to know above this point, I want to know all the percentages to the right of that point. If I want to know below, below means left, above means right, okay? Of that whatever point you're talking about. So those are going to be important vocabulary words. Let's move on. Okay, the following is a data set of baby birth weights. The doctors are trying to determine which babies were born with a quote unquote normal or healthy birth weight in comparison to the rest. This is what they found. So I organized the data set for you. They were all out of order, but the point is when we put this data set in order, we notice a pattern, right? The babies that were born with 3.2 kilograms, right? There was only one baby born that way. 3.3, there should be 2 babies born that way. 3.4, 4 babies. 3.5, 6 babies. 3.6, 4 again. 3.7, 2. And 3.8, there was only 1. Okay, so as you can see, there's kind of a pattern, right? Like if we were to graph this information into a histogram, something that you guys did, the previous week, then we're gonna get something interesting, right? And so I want to point your attention over here because these are all things that you've been doing in this class. Like the mean of this data set is 4.5. The median happens to be right in the middle of approximately, sorry, that should be 3.5. The standard deviation is roughly 0.14. I did all that math for you, so you didn't have to do it. But the whole point of doing that and having this information for you is so that we can graph it and you can visually see what happens if I were to ask you, hey, is this data normally distributed? Does that mean that is this symmetrical on all sides? Well, these numbers would suggest that they are, right? Because for every tiny baby, there is one very large baby, right? And then it's very symmetrical. So for the first section right here from 3.11 to 3.2, there's only one baby there. So there's only one there. Then we're going to do a histogram. 3.3, there's 2 babies, right? So from 3.3, the next section. 3.4 is 4 babies. 3.5 is up to 6 babies are born with that weight. 3.6 is 4, 2, and roughly 1. Do you notice anything about this, the shape that this histogram makes? If you were thinking, well, it kind of looks like the curve that we saw earlier, you'd be right. This is the origin of the curve, the normal distribution. When people were looking at data sets and the data set happened to be normally distributed, they notice, hey, it makes a pattern. Maybe we can use this to make generalizations about stuff. And that's what you guys are going to be doing. So we're going to move on, right? But just know that in this example, right, when doctors looked at this, they noticed, hey, most of the babies are born at roughly 3.5 kilograms. And most of those babies turned out okay they didn't have any like weight issues as they were in the baby stage. So this is what they would consider normal baby weight. I'm putting quotes around it because it's, that's not necessarily true, but mathematically speaking, you know, that's what it is. That's what you would expect a baby to weigh, right? This is roughly the this is roughly the mean, right? Because it's in the center, right? And then we notice that the sections below are separated by what we call the standard deviation. When we took the standard deviation of this whole data set, we found that it's 0.14, right? So if the mean is approximately 3.5, right? I'm sorry, 4.5 or whatever it was. I think I made a mistake there. Um, then what that means is that each section below it is one standard deviation away, which means that if this is the center is 3.5, then this next point is plus 1 standard deviation. What that means is if the standard deviation is 0.14, that's the difference within the groups. That means that if your baby weighed a little bit more, right? If your baby weighed approximately 3.64, you're still within one standard deviation. Your baby would be a little heavier than normal, but they're within one standard deviation, which means that they're fine, right? This is -1 standard deviation, right? And we subtract it, so this would be, let's see, 3.36. So if your baby weighs anywhere between 3.36 kilograms and 3.64 kilograms, they're considered within one standard deviation, and that's normal. That's this whole section right here. They're considered, I guess, quote unquote normal, right? They're fine. That's the weight that we expect to see, anywhere between them, right? If they're born within 2 standard deviations, they're in either direction, right? They're less normal or abnormal, right? It doesn't necessarily mean that there's something really wrong. It just means that if your baby weighs approximately like 3.3 kilometers, according to this data, right, they might be a little underweight, right? And they're not too underweight, but in general, this may suggest problems, right? And if they weigh a little bit more, if they weigh somewhere between 3.7, it's the opposite. They're a little heavier than normal. It's a bigger baby. Still, probably no problems yet, but it's something that they can keep out lookout for, right? Doctors might want to check up on them a little more because they're 2 standard deviations away from the curve, right? Away from the mean. What if your baby is in the 3 standard deviations? That's, I guess you can consider that rare, because that's not necessarily normal. Like if they're born really underweight, maybe they were, I don't know, premature. Or if they're born really big, maybe they're just a little bigger than normal, right? It could be nothing, but the doctors definitely want to look at babies they want to give more attention because there's only one kid in each section. That suggests that there's less and less. And there's sections beyond that, right? Anything beyond 3, though, standard deviations away from the mean, is such a small percentage that it becomes rarer and rarer and rarer until it gets near 0, right? So, you know, there's like the super rare cases, and then there's the not as rare cases. You're trying to determine normality within a data set, and you're going to use everything you've learned up to this point to do that. Okay, so I know I just threw a lot of information at you. Pause the video if you need to. If you didn't get all that, make sure to go back and get it. Here is how you're going to do it. When a data set is normally distributed, we're allowed to use certain properties to make generalizations about it. The properties are as follows. It's all of these things. Make sure you write them all down. If a population is normally distributed, that means that there's an equal amount of people or whatever you're measuring in each different section, right? Then you have a normal curve. And if you have a normal curve, you can make generalizations. For example, about 68% of all the data of all whatever you're measuring falls within one standard deviation. Now, there's that word again. There's that word within, right? If you notice here, I'm down here now. 68% of all data. That means most of whatever you're measuring is going to be in the middle. It's going to be near the mean, right? Now, if you notice, there's certain percentages, right? You see this percent right here? I know it might be hard to see, but these two are 34% each, right? The mean is in the middle, and this is going to be plus one standard deviation, and this is minus one standard. These are borders, right? I'm going to put a dot here. I'm going to put a dot here to represent what it is. If the mean of this curve or whatever is like, I don't know, 100, and the standard deviation is 15, let's just say it's 15, right? Then what's going to happen is I'm going to add 15 to the first dot. I'm going to end up with 115 as this dot. If I do two standard deviations, that's 2 times whatever the standard deviation is. 2 times 15 is 30. And I'm going to add that to the mean, which is 100, and I end up with 130. This dot represents 130 of whatever it is I'm measuring. This dot is 3 standard deviations away, which means it's 3 times my standard deviation. That means 3 times 15. That's 45. 45 plus the mean is 145. Notice that these dots are on top of the curve. They're not inside the curve. They're on top. And the numbers on top will change depending on the problem. But the percentages inside will never change. You see how it's 34, 34, and then the next section, it's smaller? It's like a steep curve. This is 13.5% within. So any number, or the numbers between 115 and 130, all those numbers represent 13.5% of the data, right? The numbers in between 130 and 145 represent 2.35% of the data. That's 2.35%. Yes, there's a decimal, and the decimal is a percent at the same time. The last part, the smallest part, is 0.15%, right? That's less than 1%. That's like a fraction of 1%. That's anything past 3 standard deviations. It's a really, really small percentage, right? Anything past 3 standard deviations is super rare. Right, why don't we go the other way? I'm gonna mark the top of the curve. If the mean is 100, and this dot right here that I'm making darker is minus 1 standard deviation. That means I'm gonna subtract the standard deviation. So 100 minus 15 is gonna be, let's see, 90, 85. And 2 standard deviations, it's 2 times 15 is 30, and subtract 30 from 100, I get 70. And this dot right here, I know it's kind of hard to see, would be, right, 55, yeah, 55. And then the 0.15 is referring to the area inside the curve. So percent refers to the area inside the curve, and the dots represent whatever you're trying to measure. That's going to change with every problem, whether you're measuring a test score or whether you're measuring something else like, I don't know, the weight of pennies. That's all going to change. So your job when you're labeling this curve is to change these numbers on top. These are the numbers that you're in charge of, right? Those are the numbers that are going to change. The percentages are not going to change. And if something is within 1 standard deviation, it represents 68% of all the data. What that means is 34 plus 34. Added together gave me 68. That's the percentage that's within minus 1 standard deviation and plus 1 standard deviation of the mean. Plus or minus 2 standard deviations of the mean represents 95% of the data, which means I added 13.5 plus 34 plus 34 plus 13.5 to get 95% of the information. That's within 2 standard deviations. Within 3 standard deviations, right, I added all the percentages in between the third points. That's 2.35% plus 13.5% plus 34 plus 34 plus 13.5%, plus 2.35%. And I ended up getting 99.7%. And then the extra 0.5 and 0.5, we don't count it because past 3 standard deviations, it's, again, really rare, right? And of course, the mean is in the center. The whole curve in its totality equals 100%. All right. This is the normal curve. You're going to be using it a lot. Okay, how do we solve the problems using a normal curve? Every problem that you're going to do this is going to have like, it's going to have something in bold. It's going to have letters in bold, and it's going to be the given. The given can be the same for multiple problems, so just be aware of that. Given, the masses in grams of pennies minted in the United States after the year 1982 are normally distributed. If they say that it's normally distributed, that means you can use the curve, and they want you to use the curve. With a mean of 2.5 grams and a standard deviation of 0.02 grams. All right. When they're making pennies, when they're minting them, sometimes there's mistakes. So not every penny weighs the same. What they're trying to say here is that after 1982, most of them are pretty normally distributed. On average, most of the mean was 2.5 grams for all the pennies minted after them. And they varied by roughly 0.02 grams. Some pennies were 0.02 grams heavier, and some pennies were 0.02 grams lighter. Okay, now the problem, right? So what? That was information. What's the problem? The problem is they want you to find the percent of the pennies that have a mass in between 2.4 grams and 2.54 grams, 2.46 grams, and 2.54. Okay, what should you be thinking? The interpretation part is what you should be thinking. Since the mean and the standard deviation are given, that's information we have, you will need to use the properties of the normal curves to figure out what percentage of pennies are in between them. These are your steps. When I ask you during the warm-ups, what are the steps? These are the ones you're going to write. Step 1, draw your normal curve and label your percentages, mean, and each point after that. Okay, so I'm going to do number 1 before your eyes, all right? So this is what you should always do in the beginning of all these problems. Start by just drawing a curve as best as you can, right? This is something I'm drawing on the computer, so it's a little hard. The mean is always the center. Do we have the mean? Yes, we do. They told us. Our mean is 2.5 grams. So I'm going to write 2.5 right above the first line. Okay, now we have to draw the rest of our lines because we have to separate out the curve. We have to do plus 1 standard deviation. That's terrible. Okay. All right. Plus 1 standard deviation and minus 1 standard deviation. Okay. Okay, so I'm gonna put dots above them. Okay. So I know that there has to be a value on top and there has to be a value on the bottom. I'm gonna do 2 more sections. 2 more sections on each side because there has to be a plus 2 standard deviation and there has to be a plus 3 standard deviation. There's a minus 2 standard deviation and a minus 3 standard deviation. Do you guys notice a pattern? To the left of the mean, it's all negatives. To the right of the mean is going to be all positives. And that's on purpose. Okay. So far, I've drawn my curve. Now, I want to put my percentages in so I don't forget. This is 34%. This one represents 34%. Again, these are not going to change, which is why I'm labeling them. 13.5%. This one is going to be 2.35%. And then this little section is going to be 0.15%. These are approximations. We're going to use these in class. 13.5, 2.35%, 0.15%. Okay, so I've drawn my curve. So what? What do I do? That's I did my mean, and I drew each point after that. I also did my percentages. Okay, so step 2, mark the point that represents 2.46 grams and 2.54 grams on your normal curve. Okay, so that sounds like those sounds like they're values, right? Because those are grams, and grams are the pennies that we're measuring, so those are the values. Therefore, they go on top of the curve. They go where those dots that I drew, right? These dots, I drew terrible dots, but they're here. Each one of those dots needs a value, and we're gonna start with the only value we know. It's that the mean is 2.5. That's why it's in the center. And the standard deviation is 0.02. So if we're going to do the first one, right, plus 1 standard deviation, mean plus 1 standard deviation, right? So that means it's 2.5 because we know that, plus 1 times my standard deviation of 0.02. Which means that this becomes just 1 times 0.02 is going to be 0.02, which means that this is going to be 2.52. This dot is represented by 2.52. If we want to make this a little clearer, we can say that that's a 0 right there, 2.50, 2.50. This is 2.52 grams. These are all grams. Grams, grams. The next one, mean plus 2 standard deviations, right? Again, we're just going to start with 2.5 plus 2 times 0.02. Now, this becomes 2.5 plus 2 times 0.2. We're just going to double it. So it's going to be 0.04. Hey, look at that, 2.54. Isn't that what we wanted? 2.54. I'm going to go ahead and mark this real, so it stands out, real dark, so it stands out, right? Because that's one of the points. Remember, step 2 is to mark the point that represents 2.46 and 2.54. Well, I found 2.54. Let me label the rest of them. As you can see, we're going to go up by the standard deviation with every time. And since we're adding, I'm just going to add 0.02 to the previous one. So 2.54 plus 0.02, we end up with 2.56. Now, let's go on the other side. On the left side of the mean, we're going to end up subtracting. We're going to do the exact same thing that we did here, right? But instead of adding, we're going to subtract. So instead of adding 0.02 to 2.5, I'm going to subtract them. So 2.50. You can always do this on the calculator, but I'm just going to do it here. Right? This ends up being 48. 2.48. Right? We always put the number on top, the bigger number first. 2.48 grams. Right? This is minus 1 standard deviation. The next one would be 2.46 grams because we're going down by 0.02 every time. And the 2.46 is important because that's what they were asking us in the problem. So I'm going to mark it real dark. The other one, 2.44. We're not going to need that, but it's there. Now my curve is complete. Right? It's complete. We're going to move on to step 3. Since the problem used the keyword within, you will need to add all the percentages that are in between, that's supposed to say between, in between the 2 points. Man, I need to fix that. I did not spell correctly. You marked in the previous step. Your sum is your answer. Okay, so what that means is we're going to add the percentages. This is 13.5 plus 34 plus 34 plus 13.5. I don't go past those two that I marked. Since they said within, I want the percentages that are inside. I'm going to add all those up, right? So let's go ahead and, oh no. Okay. Oh, scared me for a second there. All right, let's go ahead and make some room. Okay. And let's go ahead and add them. So 34 plus 34 plus 13.5 plus 13.5 And I guess you can write 34.0, right? So these add up to 0, carry the 1, put the dot, because the dot goes straight down. 4 plus 4 is 8, 9, 10, 11, 12, 13, 14, 15. Carry the 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. Hey, look at that. 95. If I add up all those, I end up with 95% is my answer. And that's it. The answer to my question, find the percent of pennies that have a mass between 4.6 and 2.54 grams. 95% of all pennies minted in the United States after the year 1982 are going to have a grams between 2.46 grams and 2.54 grams. And that's pretty much what you're doing. If you're confused, it's normal. When I first learned this, I had no idea what was going on. So if you understood this the first time, then guess what? You are probably within +3 standard deviations of students who understood this the very first time. If you are 100% lost, maybe you're on the other end of the curve, right? This is where the saying ahead of the curve comes from, right? If you're ahead of the curve, you're probably within 3 standard deviations. If you're slightly ahead of the curve, 2 standard deviations above the mean. If you're right on the curve, you're probably 1 standard deviation above it, or maybe even the mean, right? Okay, so if you didn't get that, you will by the end of this lesson. All right, so what happens if the problem is asking us about above and below? Let's pretend that we have a problem, and the problem says that a bunch of my students took a math test, and the average, I'm going to circle the average. Remember that X with the little hat on top? It's referring to the average. At least in statistics it is. The average score in a test that I gave, right, is 78, right? Most people scored on average, the mean is 78. The standard deviation is 5 because I took all the scores and I calculated the standard deviation, right, to see how far away everyone was from each other. You're not going to have to calculate the standard deviation for these problems. All that you did, right, from 2 weeks ago, I'm just going to give you the standard deviation for all these problems that you're going to do. However, I drew my curve, I have my percentages, and I have my mean. My mean is 78. What if I wanted to know as a teacher how many students, what if a student came up to me and was like, what was my score? And then I tell them, and they're like, oh, cool, is that good or bad? And I can tell them where it lies on the curve, how many people scored above or below their score, right? If the standard deviation is 5, I'm going to mark each point on my curve. I'm going to label these points. So +1 standard deviation, 78 plus 5 is going to be 83. +2 standard deviations, 2 times the standard deviation of 5 is 10. 10 plus 78, 88. 3 standard deviations from the mean. 3 times the standard deviation of 5. 3 times 5 is 15, right? And 15 plus 78 is going to be 93. Okay, what about to the left of the curve, right? Because remember, I'm comparing the score to everyone in the class. So 78 minus 1 standard deviation, going to be 73. 68, and wait, that's not right. Wait, is it? Yes, it is. This is 63. Okay, so if this is the distribution of all the grades, of all the test scores, of all the students in my class, right? And someone came up to me like, what did I get? And I tell them, oh, well, you got an 88 out of, let's say it was out of 100. And they're just like, and I'm like, don't worry, I curved the score, which means that it's not out of 100. You're only gonna, your grade is gonna be based off of how everybody else did, right? And they're like, oh, cool. So an 88, is that good or is that bad? I'm like, well, the mean is 78, and 88 is, and what you scored above the mean, which is a good thing. And if you want to know how many people scored above 88, above refers to the right of whatever point you're talking about. And in this case, the point is 88. So if the student got an 88 on this test score and they want to know how many people did better than me, well, I can tell them. I can tell them the percent, right? I'm going to take the numbers, the percentages that are above this point to the right of this point. I'm going to add them together, right? 2.35 plus 0.15 is 2.5%, meaning that I can tell the student, well, yeah, you did great on the test because only 2.5% of the class did better than you, right? They scored above your score, which is pretty good, right? That means that they're high up there. They're within 2 standard deviations, which is pretty good. What if a student came to me and was like, okay, what did I get? And I was like, you got a 73, right? They're like, oh, is that bad? I'm like, well, it depends how you want to look at it. The average score was a 78, and the 78 translates to like a C, right? A 73 is 1 standard deviation away, so it's not that bad. You're pretty close to the middle. It's probably 73 is probably a low C, right? So they're like, okay, well, I still don't understand. How many people scored lower than me, below a 73, right? Let's say they're that student and they want to know that. Well, how many students scored below my score of 73? Well, I'm going to take all the percentages to the left of whatever point I'm talking about. In this case, I'm talking about the 73, and I'm going to add them together. 13.5, 2.35, and this is 0.15. These are all percentages. I'm adding them up. 5, 6, 7, 8, 9, 10. 3, 4, 5, 6. Look at that. And then I can say, I can be frank and I can be like, okay, if you really want to know, about 16% of the class scored below you. And then the student might freak out and be like, I did really bad. Huh? I'm like, well, you could have done better. But you didn't do that bad, right? There was still a lot of people that scored below you, right? And at the same time, the student who got an 88 would like, can ask me, wait, does that mean how many people scored below me then? Remember how this person scored 2.5%? Only 2.5% of the people scored above? Well, I can take that number and I can subtract it from 100, which pretty much means that 97.5% of students scored below this point. And I'm going to get that by adding 13.5, 34, 34, and the other 3 if I wanted to know below, right? These are the interpretations that you're going to have to make. Above, below, within. The percentages inside the curve are never going to change. It's the values on top of the curve that you're responsible for. You always want to draw the curve first, label everything, start with your mean, figure out the standard deviations above and below, and then you can figure out, use the keywords. Are they asking for above, below, within? Then add the appropriate percentages, and that should be it. If you're still confused, please talk to me. Send me an email. If you want to do like a Zoom appointment, just send me an email to this email. Just send me an email to dpalacios@laedcorps.org, and just give me your name. Just say, hey, um, I want to schedule an appointment. What time works for you? And then I'll tell you and then I'll work out whatever time works best for you. The reason why I'm doing it by appointment is because I'm not always at my desk, especially when I'm on site and I'm teaching and I'm going around South LA helping out students. I'm not always at my computer, and I've missed a couple of people who attempt to go into my Zoom because I'm helping somebody else and I don't see it because I'm not at my computer. But if you send me an email and you're like, hey, I need help with this, can we set up a Zoom time? We'll set up an appointment that works for you, and then I can help you personally for one-on-ones. Okay. Good luck, guys. You're almost there. Keep up the good work.